Hi, everyone. This is my first time here in Oslo, so thank you for coming. And before we begin, let me see a raise of hands. How many of you have heard about event sourcing and CQRS before? Wow, that's a nice show of hands. Well, keep your hands up, please. How many of you have implemented a system using these patterns? Cool. So I hope I will teach you something new today. My name is Lidan, and I lead the user notifications platform team at Wix. A long time ago, I think it was 2010, I consulted to a startup that wanted to organize the photos that people uploaded to Facebook. And the idea was to aggregate all the photos that were taken at the same location or at the same event so that people can discover them easily on the social network. Now, remember, it was 2010. There was no Instagram or Snapchat. One of the hottest buzzwords those days was social network. Everyone did it, at least they thought they did. And we also tried to build a social graph on top of those photos that connects people, locations, events, and photos. So we started to build a network. We used MySQL as database. We had a table for locations and a table for photos and events, and a table of relationships that connects them all. So I asked them, guys, how are you going to query that table in large scale? And they were like, we don't know yet, but don't worry. I left a couple of months later, and when they started to grow, they spent thousands of dollars to maintain this unusable, super expensive structure, instead of using a better structure for this use case, like a graph database. In the long run, they didn't survive. But this story is an excellent example of accidental complexity. We model our data in some way, and when the requirements change and the model doesn't fit anymore, we work very hard to maintain it, instead of using a better structure that is more suitable for the new requirements. And the wrong kinds of models can cause us a ridiculous amount of accidental complexity. And today, I'm going to talk about this problem, and I'll show you how event sourcing and CQRS can help you solve it. A few years later, I joined Wix as a backend developer in the CRM platform team. And Wix is an Israeli company that offers a website builder that allows you to create stunning websites effortlessly. You just drag and drop elements to your site, like building a PowerPoint presentation. And we also offer more than 300 applications that everyone can add to the website. Wix builds some of them, and you can see some examples here. And there are also third-party applications. In the CRM platform team, we build tools for SMBs, small, medium businesses, that help them to grow and manage their businesses online, such as contacts, chat, and invoices. And when I joined the team, it was the early days of the Invoices project. And the idea was simple. The business owner goes to the app, issues a new invoice, and sends it to the customer. The customer receives that invoice and pays it online, for example, via PayPal. The business owner can always manage the invoices and track what was already paid, what hasn't been paid yet, and see the overdue invoices. Now, we are all developers, right? So given some mockups, we know more or less 90% of the work. Okay, you don't need the product manager to say, the save button should save the invoice in the database. So we started to design the solution. It's a classical layered architecture. There is a REST endpoint that handles requests that are coming from the client, passes it to the business logic that does some magic, and saves it in the database through a domain model. So the user creates an invoice. He fills in the form, clicks on the Save button, and then we make a post request to the server. We think really, really hard what to do. We make a decision, and we store that decision in the database. This is how a new invoice is saved. After some time, the user realized he had made a mistake. So he goes to the invoice, he edits the details, and clicks on Save. Again, we think really, really hard what to do. we find the relevant record in the database and change it in place according to the user's request. And you probably noticed that when the system is designed like this, we lose data by design. Okay? It's not a security issue or a technical constraint. This is how the system is designed. And while this architecture might be perfect for some applications, mostly because of its simplicity, it cannot be used by financial applications. Why? Regulation for Wix and also for its users. By law, we have to give our users the ability to track every action that was done in their invoices. Another requirement was scalability. Wix has more than 120 million users and 5 billion requests a day. Okay? And every invoice is viewed by the users of our users. So we are talking about large numbers, and doing it right is challenging. Obviously, we can add more and more servers, but it has a cost. And of course, as a leading company in the web industry, we want to be flexible and be able to add new features quickly and easily. So we thought about new ways to design the system to satisfy these requirements, and we started researching best practices in different industries. There is one industry that is prominent in regulation and scale. Can someone guess what it is? Does anyone here think that when he or she withdraws money from an ATM, a record in the database changes? And what's interesting for me is that it's not only the banking industry that took this approach. Every single mature industry that you look at is naturally event-sourced. Financial, medical, insurance, legal, all of them are conceptually event-sourced. And that's what naturally brought us toward looking at event sourcing for our invoice management application. Event sourcing is a way to model your data that doesn't store the current state, but rather a sequence of events that led us to this state, starting from some initial state. And we can always restore the current state by replaying the events and derive it from them. Of course, we cannot do it oppositely. In this approach, every action in our system is expressed by the domain language. And we have two basic building blocks. We have commands and events. A command is an external request that is coming to our system. It is always expressed in imperative language, like create invoice, delete invoice. It represents the user's intent to do something in our system, and it may have a payload with some relevant details. Notice how meaningful the command is compared to HTTP language, like create invoice versus post/invoice, etc., etc. After validating the command, it is transformed into a chain of events. It can be one event or more that represents facts, something that happened in our system. And like the command, the event may also have a payload with some relevant details. And the event name is always in past form, like create invoice, invoice created. Delete invoice, invoice deleted. Okay? And events are immutable. They never change. So let's say you're a business owner. You created an invoice, and you made a mistake. Now you want to delete this invoice. So what do? You issue a command of delete invoice command. And this command is transformed to invoice deleted event. But the invoice actually was not removed from the system. It's just marked as deleted. It's a logical delete. We are stating actions taken from the language or the business domain. These are not SQL statements like insert or select, and not functions in your favorite ORM. The language is universal among everyone involved. Whether a developer or a domain expert read this sequence, they will get a full story, and they will easily understand it. After transforming the command to events, we store the events in the database with a fast insert operation. And the events are the single source of truth of the system. As you can see, the database doesn't hold the current state. Rather, it holds the sequence of events that led us to this state. And the benefit here is that instead of writing down our decision, we are writing down what the user wanted from us. When a user wants to view an invoice, it's also called the current state, referred to as an aggregate in DDD, domain-driven design. We retrieve the events of that invoice from the database, and we apply them one by one and rebuild the finalized state that is eventually returned to the user. And for those of you who are familiar with functional programming concepts, you can think about a state as a left fold of the previous behaviors. In each iteration, the event changes the current state of the aggregate, and after iterating all the past events, we return the state to the user. So now when we store every single action, and we are able to rebuild the current state from those actions, our system is regulatory compliant. But more importantly, we are not losing data. And the whole system is described by the domain language and not in the language the technology forced us to use. But now we have a problem. If we only store events, how do you query them? Well, I have an idea. Let's replay every event that was ever stored in the system. This will be fast, right? So let's talk about queries, and more importantly, querying at scale. If we examine the distribution of flow between read and write operations in web scale application, most systems have more read operations than write operations that actually mutate the data. More or less, it's around 90% of them are read operations. And when we design a system in large scale, we tend to bind the read and the write model, despite the fact that in most cases, they are totally different. It is much easier to scale read requests of immutable data than write requests. We don't need to manage complex locking mechanisms or handle inconsistencies. And besides that, most of the time, we don't want to read the data in the same form it was written in. Okay? How many of you have large, complex SQL statements like these in your application? Come on, don't be shy. We all have it. I just look in this query, and the only thought that comes to my mind is, what the hell is going on here? So CRUD is difficult to scale, but we have more considerations, like normalizing the data to support new features in the future, like full text search or graph capabilities. They are not supported by the current data store. Do you remember my story from the beginning? So in fact, what we need to do is to separate the process of updates and the provision of queries. And this pattern is called CQRS. Okay, stands for Command Query Responsibility Segregation. In most of the event store systems, you usually don't query your events. You end up with a concept called read models or views. So every time a new event is written to the system, it may also update a view. And a view is a read-optimized set of data that is used to make the reads faster. It can be a denormalized, pre-aggregated table in MySQL, but it doesn't have to be relational. Actually, you can use a JSON file, Elasticsearch schema, and it's not necessarily stored in the same data store like the events. Okay? You can use different data stores for different kinds of view. And this pattern allows us to see our data from different points of view. when a new requirement comes, we just add a new view to the system and build it by replaying the events from the beginning. So when you work this way, you cannot change what happened in the past, but you can have a new perception of what happened in the past. And I'll give you an example. This is a screenshot from our invoice management application. And you have the numbers on the top. You have paid, sent, and overdue. And actually, it is stored in the database in the same form you can see it here in the user interface. We have the same columns. We have paid, sent, and overdue. And, of course, another column that identifies the tenant. And also, for the table below, the table of the invoices, we have the same table. In MySQL, we have another column for the tenant identifier. So it looks simple, but it introduces you new ways to design and architect your systems. For example, you can execute the read and the write model in the same service or separate them to different services and different databases. And when you have two separate services, you can scale each of them independently. Okay? You can deploy the write model in your own data center and move the read model to the cloud. But when using this pattern and separating the models, you should take into account the inconsistency window between writing the events to the event store and updating the views accordingly. And you lose the strong consistency, and you end up with eventual consistency. And while some applications can live with that limitation, others cannot. So it depends on the business requirements. One more thing about CQRS is that you can use CQRS pattern without event sourcing, although they naturally go together. And I'll give you an example. When you publish a Wix website, we create a special site that is highly optimized for our viewer application. And it is stored separately from the editing model. We have the editing model and the viewer model. And it allows us to separate Wix to two different segments. We have the editor segment, and we have the public segment. And each segment has its own scaling policy and SLA policy. So you can use CQRS without event sourcing, and that's totally fine. Remember that CQRS is an optimization. Okay? And like every optimization, beware of doing it prematurely. It is difficult to do it well, and it makes the system more complex. So please, don't try to solve problems that are probably not existent in your system. Okay? And out of everything I would say today, this one is probably the most important. I would suggest you consider doing CQRS when you really have scaling issues in the system. And when the distribution of flow between read and write operations is highly asymmetrical. For example, in the invoice management application, we started by reading the events in every read request and building the views in memory. And when the applications grew and scalability started to be an issue, we changed some views to be persistent, and that improved the response time of the read model. So eventually, we came up with the following design. So when a user wants to send an invoice to his customer, and the client issues a command and send the invoice to customer, and then it makes a post request to execute endpoint. And then we pass this command to the command decoder. The command decoder is responsible for the deserialization from JSON object to JVM object. So we can do some validations, and we will touch the validations soon. And then it is passed to the command handler. And the command handler is responsible for transforming the command to events. It can be an event or a sequence of events. And then we first store the event to the event store, and then we publish it to the event bus. And we have multiple consumers of that bus. We have analytics for BI, and we have emails. It is consumers that actually sends the invoice to the customer. And we have a rate optimized view. For example, the table of invoices I showed you earlier. We just update the status of the invoice from draft to sent. So this is the right flow. Obviously, it's very high level. And the rate flow is very, very simple when you work this way. We just go to the endpoint, invoice with the invoice ID, and then we just go to the read optimized view. We fetch the relevant view and return it to the user. We have another arrow, we will touch it soon, that updates the view during the read process. We just compare the version from the event store and the view, and if there is a gap, we update the view and return it. It's like a self-healing mechanism. So now, by using the CQRS pattern, the system can run in large scale, and we can add new features easily by creating views. But basically, we got more than that. First, since we store every user's action, we got an audit log for free and by design. Every change in our system is logged in accurately. And because we are relying on it as a source of truth, we are more confident to use it than a regular text file. That's actually a very powerful tool. You can use this log for different purposes. For example, for testing purposes. If you want to understand what led the user to the current state, like a debugging tool. So you can also use this audit log. You can also take those events and replay them in different environment, in different data store, isolated from the production environment. If, let's say, we want to test a new feature, and we want to test it on the existing data, we can just take this feature isolated from the production environment and replay the events with a new feature. Actually, we can restore the system to some point in time by replaying the events until that point. So if you want to know how an aggregate looked like a few weeks ago, you can just do it. And you can not only restore the data, but you can analyze historical data that would be lost if we didn't use event sourcing as our data model. For example, whenever you come up with a new idea or new algorithm to analyze your data, you can just update the event handler and then replay the events from the beginning. And this is a very powerful tool. And trust me, your BI analysts will thank you for that. Another interesting feature is the ability to create different schemas according to the system requirements. And the event stream is the single source of truth of the system. And views are derived from it. Think about it. At any point in time, I can blow away my views completely and rebuild them from the events. This ability makes it easier for everyone in your company to consume that event stream and build their own view of the world. So I'm looking at you, and you probably think, silver bullets, right? Too good to be true. So I'm going to tell you a secret. Event sourcing and CQRS are not magical solutions for your system. As you probably know, choices of architecture are never good versus bad. It's just a trade-off at some context. And you must take into account the complexities of every solution you choose. Okay? It's not necessarily relevant to event sourcing and CQRS, it's relevant for every architecture and every system you build. Some challenges are raised only when you work on a real application with real traffic and real business behind it. And those challenges can appear in two different forms. Number one, the development model is unusual, especially when you work with separated read and write models. It feels strange at the beginning. There is a learning curve, but it's not that hard to get used to it. But let me ask you a question. What do you prefer? A very thin layer that handles commands and events, or a very complex database schema that restricts the queries you can run? Now, after separating the read and the write models, you can work with different data stores for various models. Well, how do you manage them? How do you do backups? What about monitoring? So during the development of Wix invoices and some other Wix products that used our event sourcing infrastructure to manage their data, we encountered three major challenges. How do you keep your views in a consistent state? Does your application has to be fully consistent, or can it be settled for eventually consistent? Eventual consistency means the data doesn't have to be consistent all the time. The only guarantee is that data becomes consistent at some point in time, eventually. And for most applications, eventual consistency is sufficient, but there is no single solution for that. Again, it is always a trade-off between consistency and performance. Okay, it's based on the business and the domain requirements. So first of all, we can build a fully consistent system by replaying the events in every read request and building the views in memory. The disadvantage of this approach is the strong binding between the read and the write model, which makes it harder to scale the system, especially when you work with complex views. Another possible solution is to do CQRS with synchronous writes. You don't have to use a heavyweight distributed bus like Kafka in order to update your views. You can just do it synchronously. In this approach, we have all the benefits of denormalized, read-optimized views, but the writes will be slower since we need to update multiple views. So we can do it better. And a better solution might be comparing the current version of the view with the current version of the event store. And if there is a gap between them, we update the view and return it to the user. So these are the main three solutions of handling views inconsistency. And of course, it is tunable. You can choose the consistency level per view. And you can also mix these methods. It depends on a view. Consistency is a product concern, not technology. And this is a very important point. And most of the team don't do this conversation with the product manager. They just choose the consistency level by themselves. So I'm really sorry, guys, but it's not our business. Just give the product manager to decide and do it. So the next topic is validation. How do you validate the commands in your system? And validations come in different variations. We have a different level of validations. And the basic level of validation is validating the payload data. For example, string length or numbers range. And in Wix, we use a CRUD for this kind of validation. A CRUD is an open source Scala-based library that allows you to validate input data easily with a very, very simple DSL. And you can see an example here. Even if you don't know Scala, the syntax is very simple. And this is the first stage of the validation process. We can also verify that a given command can be performed on the current state of some domain entity. For example, the application cannot handle update command if the aggregate was already deleted. And for this use case, we mark these special commands, delete, create, with Scala trait. Scala trait is like a Java interface. And when we handle the command, we check its type against the current state of the aggregate. And what about more complex validations? For instance, let's talk about uniqueness. Imagine that you are developing a contact management system. Okay? How can you make sure that there is only one contact per tenant with a given email? So a possible solution for this use case is creating a special persistent view for this validation that contains all the emails that belong to some tenant. And on the validation phase, before transforming the command to events, we check if the given email already exists, and if it does, we'll throw an exception. And I know, some of you may probably notice that a validation that is based on a view may raise inconsistency problems, and you're basically right. Again, it depends on the business and the domain requirement. Some systems can live with this invalid data once in a million writes, but others cannot. And you should take in account when you design a system using CQRS and event sourcing. The last thing I want to talk about is concurrent writes. So let's assume that two commands were written at the same time. Update invoice and delete invoice. What would be the state of this invoice eventually? So one solution is to use pessimistic locking. So only one command per aggregate can be handled at the same time. Once the first command takes the lock, any other command will wait for the lock to be released. And this is the safest way to prevent concurrency issues, but obviously it's the slowest and most complex way. We need to manage distributed lock and handle timeouts. Yuck. So we have a much better solution. So let's talk about optimistic locking or versioning. So each event or the aggregate has a version. It is incremented by one every time a new event is written to the system. The version of the aggregate is the version of its last event. And in this solution, each command has the expected version. It is the version that the aggregate was when the command was issued. And in case of a gap between the expected version and the current version, we'll throw an exception. We can also resolve the conflict by merging the events, if possible. And let's see an example. So here we have two different events that written at the same time with the same version, but different type. In this use case, we can merge the events by incrementing one of the events by one. But in this case, we have two different events with the same type, with the same version, and they were written at the same time. So we cannot resolve it, and in this use case, will throw an exception. And you can guess that also here, the way we handle concurrent writes is based on the business requirements, not on the technology. In a content management system, we can probably merge events. We have the address event and new email event, so that's fine. However, invoice management and accounting are more sensitive domains, and merging the events may change the invoice completely. So we've talked about CQRS, event sourcing, and we've seen how to design a system using them and some challenges that you're going to face. So what have we learned at Wix in the past 3 years from using these patterns? First of all, start small. Don't try to model every entity in your system using events. That's a really bad idea. So before you go back and say, Lidan said we should separate read and write and model every entity in our system with events, ask yourself the following question. Do you really have a benefit by storing the history of those actions? Is it worth the operational cost of modeling it with events, or can you remain with CRUD? And I'll give you an example. In the invoice management application, we have a feature called tax presets. It's a tax name and tax rate, and it's a preset. Just you can use it to create invoices faster. Is this feature worth the cost of modeling it with events? What would the view look like? Tax name, tax rate, and tenant ID? So CRUD sounds like a better approach here, although the rest of the system is all event sourced. Code changes. Once an event of some type was written to the data store, you cannot remove its definition from the code base. It is always, it's also harder to make changes in the events, like adding fields or removing fields. You should always think about backwards compatibility. And remember, once events are written to the data store, they will be there forever, okay? So your code should know how to handle them, and even when you stop writing them or deprecate the events. So either do a migration plan to migrate the old events to new events, or just make your code to handle the old events. The last and the most important point, in my opinion, is that events are the fundamental source of truth. And you can always delete the views and reconstruct them by replaying the events. And this ability gives you a lot of power. You can build your user interface incrementally. You don't have to normalize your data, write complex queries, or run data migration scripts. Just remove the view and build a new one from the events. So I hope I convinced you that it's worth researching more. Here are some references that might be helpful for you. And here are some JVM libraries that allows you to build event sourcing and CQRS applications. We are working on open sourcing our internal event sourcing library. Hopefully, we will release it soon. There are also similar libraries in the JavaScript world, in .NET. And that's the whole idea, okay? It's a pattern. Patterns are language agnostic, okay? Language is implementation detail. But people are always asking me, OK, that's a very nice pattern, but we want to see some code. Give us some code examples. So let's see how we implemented the event replaying mechanism in Scala. If you have any questions about the syntax, just raise your hand. So here we have the load method. We have the tenant ID and the aggregate ID. And we can pass a revision if you want to view an aggregate in specific version. It is optional. And the first step, we just fetch the events from the event store. We have the event stream reader that just read the events from the database. And then we build the aggregate. We have the reduce function that is passed to the class, not to the method. And we have the empty state. The empty state is based on the aggregate ID. Okay? And we just map the events to the data. We just need the payload. And then after building the aggregate, we return the snapshot to the user. But this is the important line. So let's see how we implement the reducer. We have the aggregate reducer. We have the reduce method. It depends on the aggregate. So every aggregate implements its own reduce function. We have the aggregate and events, and the method returns a new aggregate. And we have the apply method that just fold left with some initial state and with a reduce function. And this is looks familiar, no? We have the reduce. Do you remember this slide from the beginning? So to summarize, event sourcing is a pattern that allows you to capture your user's intent by writing down the whole story of what the user does in your system. This pattern goes naturally with another pattern, CQRS, that gives you the power to evolve your business logic incrementally by using views. And by separating the read operations and the write operations, it allows you to solve scaling issues that may be raised when a system grows. However, like every other architecture, there are some trade-offs that you must take into account when working this way. And we've talked about them. We've talked about validations. We've talked about handling views inconsistencies and how to handle concurrent writes. So in conclusion, if we go back when we started the Invoices project, none of us had an idea of what event sourcing and CQRS are. We knew the concepts, but we had no idea how to implement them and what are the challenges we're going to face. Since then, we've migrated and implemented multiple products in Wix to use our event sourcing infrastructure to manage their data. It absolutely changed the way I think about data. Thank you very much. Keep it in your event store. So we move to your questions, I'd like to hear what you thought about the presentation and if you have any feedback. So if you'd like the slides, just go to this URL now, escqrs.online, answer a very short survey. It will take you 30 seconds. I promise you 30 seconds. Push submit, and you'll be taken to the slides. And I'm also available in Twitter if you have any questions, so feel free to contact me. And I'll be here for questions, and I have some Wix pins, so feel free to take some. And enjoy the party tonight. Thank you.